infrared spectrum, and then we're going to look at a couple of examples, okay? So one thing to note, all of these wave numbers, of which we can expect these various absorbances, I will give you these on the exam. You don't have to memorize these values, okay? So this will be a component of the actual material that I give you for the exam. Again, I only want you to focus on diagnostics. So I don't give you any of the carbon, oxygen, single bonds, any of that stuff that you would find in the fingerprint. Okay, in general though, where we can kind of expect to see things between 16 and 18, that's where we're looking for double bonds. Between 21 and 23, triple bonds, and then anything above 27 is something attached to hydrogen. So the first thing I tell you guys to do is draw a line at 1500 and look to the left of that line for any type of signal, okay? Ideally, if you find anything in between 16 and 18, you know there's a double bond. 21 and 23 is a triple, and then anything above 27 is going to be a something attached to hydrogen. Finally, the other thing I tell you to do is to draw a line directly at 3000. So we talked about 3000 being kind of important last time with respect to things attached to hydrogen, right? So if we look to the left of 3000, let's say that we had a peak at about 3100 inverse centimeters. Who was that due to? It was a carbon-hydrogen bond, but what type of carbon were we looking at where we saw something at 3100? What type of hybridization did that carbon have? So sp3 is right here at 29, right? If we were above 3000, specifically at 3100, what type of orbitals was this carbon utilizing? Not sp3, but sp2, right? So for 3100, this was sp2 hybridized carbon hydrogen, right? So this is 31. What about 33? What was 33 due to? What type of carbon was that hydrogen attached to? This was sp. So if it's sp, what has to be on the other side of that carbon? A triple bond, right? So you would know, oh, look, if we're getting a signal at 3300, that's a hydrogen attached to a carbon, but that has to mean that there's a triple bond, right? What about this sp2 carbon? What has to be on the other side of this guy? A double bond, right? So that's going to be a big indicator or indicative that there's a double bond over here. And then now, at 36, broad signal, who is that telling us about the presence of? Broad, 36, broad, 3600. Alcohol, right? So if you find something at 3600, it's probably going to be an alcohol group. It's very broad. What about that 34 to 35? Who is that?
Carboxylic acid.
Not broad. 34 to 35. It could be one or two peaks depending on whether or not the amine, right? So this guy was our nitrogen-hydrogen bond, okay? So anything to the left, we're looking for sp2 hybridized carbon-hydrogen, sp3 hybridized carbon-hydrogen. It could be an OH, it could be an NH. They all have different signal intensities, they all have different signal shapes, and they all have different wave numbers at which they absorb light. That's what IR spectroscopy tells us, yes?
And if I'm looking diagnostically at the NH, if I see two next to each other?
Two right next to each other.
Okay, that is a second degree.
Primary. Two peaks, I know it's kind of inverse, but two peaks is primary, one peak is secondary. Okay, so 1500, look for double, triple bonds, right? And then move to 3000, look for, oh, is it carbon-hydrogen? Is it carbon-hydrogen? Is it carbon-oxygen, nitrogen, hydrogen, etc.? Okay? All right, so with that, I'm going to give you a spectrum, and I give you a range of molecules with which this spectrum could correlate to, okay? I want you to tell me who the actual correct molecule is. The spectrum is from one of these. I want to know who it is. All right, so the first thing I'm going to do, like I said, is I'm going to draw a line at about 1500. So this is about 1500 on the spectrum, and I'm going to ignore everything to the right of that line, right? Everything to the right of that line is single bonds. I don't care. There's too many single bonds, too much to deal with in the fingerprint region. So now, once I look to the left of that bond, who is the first one that I encounter? Who's the first peak? So first thing I find is about this guy, right? And that's at about 16-ish hundred. All right, so we'll say 16 to 1700. Most importantly, how would you characterize this peak? Is it a strong signal or is it a weak signal?
It's a strong signal.
Is it? Strong's going to go all the way. It's going to be real far down. Compared to, yeah. So it's weak. This is what we would call weak.
So it's only weak if it like goes farther down
Like if this was strong, it would be like this. That's a strong signal, right? A weak signal, let's say, only gets about 50% of the way down, okay? Okay, so weak in that 1700 region area, who do you think it's going to be? It's not going to be a carbon-oxygen. It's going to be carbon-carbon, right? This is pretty indicative, especially this weak signal, of a carbon-carbon double bond, okay? So that's number one. How else could we find this carbon-carbon double bond? What other big indicator would tell us that? Because what hybridization state is this carbon utilizing? Hybrid orbitals? This is sp2, right? So what other big indicator would tell us that there is a carbon that's sp2 hybridized?
It's a pass.
Right, so if we looked at this bond between hydrogen and the carbon that's sp2 hybridized, where would this show up at? This would be above 3,000, particularly where at though?
Is it like 3,300?
3,100 for a carbon-hydrogen bond where the carbon is sp2 hybridized, right? So if I go over here to 3,000, which is my next step in doing this, and I draw a line, what's right there at 3,100?
The same one, the same piece.
Right. So this guy is our carbon-hydrogen bond from a carbon that is sp2 hybridized, okay? So this guy, we'll say, is carbon-hydrogen, but this is sp2 hybridized carbon. Now, what about this guy to the left of that? What is this? This is a very strong signal, but how would you describe its shape? This is broad, right? And this is broad between about 32 to 36 inverse centimeters. So who is that? Broad, 32 to 36? OH, right? So this is an alcohol. It's not a carboxylic acid. How do we know it's not a carboxylic acid? Carboxylic acids would be from about here to here, right? Gigantically broad, right? Cover up everything else, okay? So we know this is an alcohol. So we know there's a carbon-carbon double bond. We know there's an alcohol group. So is it going to be 1? No. It's going to be 2? No, because that's a carboxylic acid. We said no. I told you no for this one. Again, what's the problem with 4?
It's also carboxylic.
It's a carboxylic acid, so no. And so the last one is 5, okay? Now, there's one little thing I want to note, which is kind of cool here. We found that weak signal for the carbon-carbon double bond at about 1700, right? But note that there's a tiny little bit of a peak here. So that's a little bit to the left of that carbon-carbon double bond. Who do you think that's due to? It's not strong, right? But who do you think that potentially could be from? Because this is coming in at about probably 17 to 18, right? Just to the left of a carbon-carbon double bond. Who do you think that could be from?
I want to say CC.
Oh, yeah, that's right. That would be carbon-carbon. No.
So carbon-oxygen double bonds will come in about 17 to 1800. 1680 to 1750, right? About that region, okay? Where's this carbon-oxygen double bond coming from, this molecule? It's very tiny. There's only a little bit, small proportion of it. But for this molecule, where's this carbon-oxygen double bond coming from? Is there a resonance structure that I could draw for this?
No way.
Yeah, so this is a good indicator that we do have a resonance structure for this. And in that structure, this bond is not a single bond, it is instead a double bond, right? So even though it's a small fraction of the molecules that have this, it's there. And you can see that in spectroscopy, right? So How do we know that resonance exists? Well, you just do. It's right there. It's a carbon-oxygen double bond. Okay, so one last thing I want to talk about, and then we'll be done for the day. How we can use IR spectroscopy to determine the success of a reaction. So I don't know if you guys have covered IR spectroscopy in the lab yet. No?
We don't
So,
have them measured.
well, usually they'll just give you a spectrum and be like, assign some peaks to it, but okay, whatever. You can utilize IR spectroscopy besides just trying to figure out what functional groups are present to actually track the success of a reaction. So for example, let's say I had a reaction where I was taking a reactant over here. It has a nice alcohol group, and I was trying to turn it into a ketone. I was trying to oxidize it to this ketone. How could I utilize IR spectroscopy to tell me whether or not this reaction had been successful? So we have reactant going to product. What type of signals, if I had taken, let's say, my sample of reactant before anything had happened, what type of signals could I expect in the IR spectrum for this alcohol?
Well, it would be less than 3,600.
So again, just in the diagnostic region, there's no double bonds, so we're not going to find anything. There's no triple bonds, right? But what should we expect to see, particularly due to that OH group? A very broad peak. So we could say, okay, there's going to be a broad peak at about 32 to 36, which is due to the presence of this alcohol, right? This OH bond. Let me erase this. Am I recording this? Okay. OH, this guy, okay? So we can go in, we can take a sample, take a picture, or take a spectrum of our reactant, right? We can take it out, we can do the reaction, we could work it up, we could purify it, and we can take a picture or take a spectrum of the product. What's going to happen comparatively in the product if we looked at it via IR spectroscopy? Specifically, in the reactant, we had that broad peak. Is that going to be there if the product, if our reaction was successful? Is that broad peak at 32 to 3,600 going to be present in the IR spectrum of our product if our reaction was successful?
Apparently not.
No, right? So one big indicator, there'd be no peak at 32 to 36. Right, so that would have completely disappeared. There's no more alcohol group. What would have come in instead that wasn't there in the original spectrum? Right, so instead we would find what type of peak, or how would you describe this peak? It would be a strong peak. And again, we could go back and consult our little table to tell us where we could expect to find this ketone, but where would we expect to find this ish? Carbon-oxygen double bond, about 1,700. Was that strong carbon-oxygen double bond at 1,700, was it present in our initial starting material?
No.
No. So again, the purpose of this, how can we tell whether our reaction had been successful? We take an IR spectrum of our starting material. It has this broad peak at 32 to 3,600 due to the alcohol group. We do the reaction. We purify, we work it up. We take an IR spectrum of our product. How do we know? That broad peak's gone, and what has replaced it instead? Strong peak at 1,700 or 1,700 inverse centimeters. Okay. So again, how do we use IR spectroscopy to tell us whether or not a reaction has been successful? We compare the spectrum. We know what we expect here to the spectrum afterwards. We know what to be able to expect there. Okay. So briefly, with the time remaining, I want you to do that. I have two reactions where I want you to tell me how you would use IR spectroscopy to determine the success of these reactions, right? So again, we're looking at what would you expect to see in the reactants that's different in the products. Okay, so we went over both of these in class. So I'm going to briefly just review them. For both of these reactions, I don't care necessarily how we're getting to the reactions. I just want to say, hey, here we have our reactant, here we have our product. How do we know whether or not we have been successful using IR spectroscopy and the peaks that we're actually going to find in the IR spectrum for both the reactants and products, okay? So what we can do is we can go through and kind of tell what type of peaks we would expect for both the reactant as well as the product, right? So for reaction A, right, when we look at our reactant molecule over here on the left, We've got a bunch of single bonds, right? So we've got a bunch of carbon single bonds. We've got a bunch of carbon-hydrogen single bonds. And then at the very end, we have this oxygen-hydrogen single bond, right? So for all the carbon, oxygen single bonds, those are all going to be found in the fingerprint region, which we're not going to utilize to help us determine structure. We will see these carbon-hydrogen bonds, so particularly these bonds, in the diagnostic region, but for each of these, this is carbon that is sp3 hybridized attached to a hydrogen, right? So we're just going to get kind of a bunch of junk in that 2900 region, 2900 inverse centimeters region of the spectrum, right? So usually, for the most part, these carbon-hydrogen bonds that are sp3 hybridized carbons, we're not going to really be able to utilize to help us determine structure, okay? So we will expect something in this region. It's not going to be super indicative of anything. The other thing that we will expect, though, in the diagnostic region is this oxygen-hydrogen bond, right? So again, we're looking at the stretching from this bond, right? Oxygen-hydrogen, we can expect to find at about 36. But as a reminder, with respect to the shape overall for this bond, we should expect a broad overall signal, right? And that broad signal is going to be between about 32 to 3600, right? So let's imagine that, we have our OH group. It is participating in hydrogen bonding. Because of that, that's going to broaden our overall spectrum, or broaden our overall signal here. And so we'd expect something between, in this region, this broad signal between 32 and 3600, okay? So for our reactant, we're going to see some stuff about 29 for those carbon-hydrogen bonds that are from sp3 hybridized carbons. And then we're going to expect a very indicative signal of that OH group, that broad signal between 32 and 3600 inverse centimeters, okay? Now, how is that going to differ if we have been successful in our reaction, right? So if we have taken our reactant and we have turned it into our product over here, how is the IR spectrum going to be different for our product, okay? So number one, again, the majority of stuff that we're looking at are carbon-carbon single bonds, right? But we do have the introduction now of a carboxylic acid group, right? So this was an alcohol. It has been oxidized, so that's what I indicate when we do this. This means oxidation. It has been oxidized to a carboxylic acid. Carboxylic acid. Right, so with the carboxylic acid, we know that because of this guy, again, our oxygen-hydrogen alcohol group, because we can essentially, or we have two different regions for hydrogen bonding in the carboxylic acid, that broad OH signal is going to broaden even more, right? So for carboxylic acids, we go from something like this to something like that, right? It's super ugly in the IR spectrum for carboxylic acids, that OH bond particularly, all right? So we're going to get an even broader, we'll go to black here, even broader signal, and that broader signal is going to be between 22 and 36 inverse centimeters for specifically this OH of the carboxylic acid, of the COOH, okay? Another big indicator is going to be from this guy, right? So this is a carbon-oxygen double bond, right? So carbon-oxygen double bonds, this carbonyl group, is going to give us a very strong signal. So we get a very deep absorbance, right? It's still fairly narrow, but strong. And we can expect this at about 1700 inverse centimeters in that area of the double bonds, right? So we get a very strong signal for that carbonyl group. We get a very, very, very broad signal for the OH, right? Again, this bond particularly of the carboxylic acid. So how do we know? Well, number one, this was not there in the reactant, and this OH group was less broad in the reactant. So we get a much broader signal in the products. So number one, introduction of this bond and a broadening of that OH stretching frequency. Okay, so then number 2, we've got our reactant molecule over here, so we'll call this B. We've got our reactant molecule over here, going to our product molecule over here. So there's a couple of signals in the diagnostic region that we will find for our reactant. Number 1, we do have a carbon-carbon double bond. All right, so carbon-carbon double bonds, it is asymmetric, so we will see it. It's not a symmetric double bond. We'll find this in a very weak signal between about 16 to 1700 inverse centimeters. Very weak signal, so a very tiny little signal with respect to the overall signal strength in the IR spectrum. We'll also find the presence in the diagnostic region of these carbon-hydrogen bonds, right? Because these carbons are sp2 hybridized, right? So this is a carbon sp2 hybridized hydrogen bond. We can expect to find this to the left of 3,000 centimeters, inverse centimeters, so we'd expect to find this about 3,100 inverse centimeters. And then finally, we also will find the presence of this nitrogen. So we've got a nitrogen-hydrogen, right? We will also find this bond, so we highlight that in the diagnostic region. This is a secondary amine, right? So we expect only 1 peak from this bond, not 2, as you would find for a primary amine. In the secondary amine, we would expect this about 3450 to about 3550, right, inverse centimeters. Okay, so now, those are the 3 things that we would expect to find in the diagnostic region for our reactant. When we move to the product, a couple of them are going to stay the same, right? So we still have our carbon-carbon weak signal, carbon-carbon double bond, right? So this guy will be preserved, right, over here. We still have our carbon-hydrogen bond, our sp2, so carbon sp2 hybridized carbon-hydrogen bond. So we'd still expect to see, for this guy, we'd still expect to see this guy. Okay, so which ones have been preserved? Highlighter. This one is preserved. This one is preserved in the product. But now the one that disappears, which is indicative that we have actually formed our product, is going to be this guy. Right, so now we've got nitrogen with no more hydrogens. So this peak, this 1 peak that was at the 34 to 3,500 inverse centimeters for that secondary amine is not going to be present in the product. So this is not present in product, okay? So how would you know? Well, everything would change except that one little tiny peak would go away in the overall product, and so you'd know if that happened that you had been successful in your reaction. Okay, and yeah, you may be introduced, for this guy, there's a bunch of carbon-hydrogen bonds. You've introduced those, but again, those are sp3 hybridized carbon-hydrogen, and again, these aren't super indicative. There's going to be a bunch of junk in that 2900 region of the spectrum. It's kind of almost like a fingerprint. It's hard to utilize data from that area. Okay, so again, you guys should be able to describe how infrared spectroscopy can be utilized to tell whether or not you have been successful in a reaction. Okay, and so mass spectrometry is not a spectroscopy, and that's why I keep NMR and IR together, and then I move mass spec at the end. Mass spectrometry instead looks at the interaction between matter and really high energetic electrons, or high energy types of particles, okay? Okay, so what happens in mass spectrometry? And so also, I don't like to say spectrometry. It's very difficult to get out. People will abbreviate this mass spec. That's it. They'll call it mass spec, okay?
But what if you called the other thing spec as well?
No one calls spectroscopy. Spectroscopy is a little easier. Spectrometry, like, I don't know, it's like spectrometry, spectroscopy. Much more harder consonants in spectroscopy, so. Nobody does that. I don't know. They must have talked about it at a convention sometime, what they're going to call it.
But it wouldn't be mass spectrometry.
It's mass spectrometry. It's hard. That's why it's people that say mass spec.
Spectrometry.
Mass spectrometry. Never mind.
Yep, exactly.
Sounds like you're saying
Astronomy, you know.
Astrometry.
Mass astronomy, you know.
Yeah. Okay, so what happens in mass spectrometry? Okay, so number one, what we're going to utilize this for mainly is to determine the overall molecular weight of a compound. So that is what mass spec is used for, is to determine the molecular weight or the molecular mass of a compound. What happens? All right, so it gets real weird. So we'll have our sample in mass spectrometry. And the first thing that we will do to our sample is we will vaporize it, okay? And so I really don't want any questions about how this happens, okay? I just want you to trust me. We vaporize it, okay? It's vaporized. It's hanging in the air, vaporized. Then what we do is we bombard it, and they love to use the word bombard, so I'm going to write that out. We bombard how do you spell bombard? Okay, bombard it with high energy electrons, okay? So we vaporize it and then we shoot at it a bunch of high energy electrons, okay? Now, what does that make it do? All right, so when it gets hit by these high energy electrons, what it does is it shoots out an electron of its own, okay? That is the basis of what we're doing with respect to mass spec. We have our sample, we vaporize it, we bombard it with these high energy electrons, and then it's going to eject an electron of its own, okay? Okay, so what do we do with that when it ejects this electron? Okay, so we have our compound, let's say. We have our nice little carbon-carbon bond here. How many electrons are in that carbon-carbon bond? How many electrons are in a bond? We've got 1 and 2, right? We take our sample and we bombard it with these high energy electrons, and it ejects one of these. How many is going to be left?
1.
Just 1 in that bond, okay? So because we have taken away an electron, we have now formed a positively charged molecule. What do we call a positively charged ion? A cation. So we formed a cation in this process. And we've also formed what's called a radical. Okay, a radical is a compound that has a single unpaired electron. Okay? So in the process of bombarding this and it's spitting out and ejecting an electron, we have formed what is called a radical cation. Okay, so this is the first thing that we form, our beautiful radical cation. This radical cation has a lot of other names to it. Okay, it has specifically the name molecular ion. Molecular ion. Another name that they call it is the parent ion. And a way that they abbreviate it is this M in parentheses with a plus and then a dot. So again, that's representing this radical cation, our molecular ion. Okay, so we're here. We've made our radical cation, right? Now, thing to note, electrons that this guy just ejected, does it really have any mass to it?
No, very, very little.
Very little, right? So for the most part, this radical cation, or our molecular ion, our molecular fragment, essentially has the same mass as our original sample, right? Because again, the ejection of an electron doesn't really do anything. Okay, so this little guy is, how stable do you think it is? Looking at this nice radical cation, we've got a bond that was a bond, now just has a single unpaired electron to it. How stable do you think this molecule is?
Very unstable.
Fairly unstable. Okay, so depending on the type of radical cation you form, depends on the stability of this. But this guy is also going to undergo what's called further fragmentation. Okay, so when it further fragments, what can happen is this radical can essentially go with one of our pieces of our molecule, right, and go away from the other piece of our molecule. So So what we're left with, as a result of this fragmentation, is a radical still, and then a carbocation. Okay, we've seen a carbocation before. Okay? This fragmentation can continue. There's a lot of different ways these various things can fragment. Okay? Now, what are we going to do with all of this? So what happens in a mass spectrometer, we vaporize it, we bombard it, we form our various fragments. The ones that are charged, so our positive charged species, are then going to be deflected by a magnetic field. Okay? So anything that is not charged is not going to be deflected, is not going to interact with a magnetic field. Everything that is charged is going to be deflected by a magnetic field. Okay? For example, this radical, is this charged?
No.
No. So this guy, we're not going to see it in our mass spec or our mass spectrum. Anything that's charged is what we're actually going to see and what we're actually going to uncover. Okay? When it's deflected by this magnetic field, the smaller the molecule is going to be deflected the most. So overall, the smaller the molecule, the larger the deflection. Also, the more highly charged the molecule, the larger the deflection as well. But for the most part, with all of these fragments that we get in our mass spectrum, we're only going to be seeing molecules with this positive 1 charge, these carbocations or these molecular ions, etc. Okay? Okay, so after they're deflected, they're measured, right? They're measured by the amount of deflection. And what the mass spectrum does is it measures what is called the charge to, or mass to charge ratio, which it abbreviates as M/Z. Okay? So we're going to get the presence of our parent ion, right? We're going to get the presence of all these various fragments that are coming through as well. These guys are all going to be, again, positively 1 charge. Okay? Now, if Z is the charge here, so Z is the charge, and that charge is positive 1, when we're really measuring this mass to charge ratio, what are we really measuring?
1 charge.
So if all of them are positively 1 charge, and the ratio that we're getting is the mass over the charge, but that's 1, what are we actually really measuring from these? Just the mass, right? So this is kind of manipulated the fact that all we're really getting out of this is the mass of each individual fragment.
And you mentioned that the mass is always what the original compound is.
No. So that's going to depend. Okay. But the original compound, the parent ion, or the molecular ion, will be present in the overall result. It's there as well as a bunch of other fragments. Okay, so great. Now, what are we going to do with that? Again, when we actually look at what a mass spectrum looks like, we're measuring this mass to charge ratio, and we're plotting it relative to what we call the relative abundance. Okay? So for example, I have put on the slide the actual mass spectrum of methane. Okay, so methane is the molecule here. Again, on our x-axis, we're looking at our mass to charge ratio, and on our y-axis, we have plotted this relative abundance. Okay, so number 1, what is the actual molecular mass of methane? Carbon is 12,
And then 1,
and then we get 1, 1, so 12 plus 4 is 16, right? So the mass here is 16, and we already know that. Okay, so when we look at this mass to charge ratio, and again, this charge is usually 1, so this is just the mass ratio, if you want to think of it like that. What is our highest peak at?
16.
16. Okay, so number 1, this was our molecular ion, our molecular fragment, our parent ion, our radical cation. That was the original one. Okay. Whatever the tallest peak in our mass spectrum is, we call this the base peak, and it's going to be defined with a percent abundance of 100. Okay, and everything is measured relative to it. So for this molecule, the molecular ion is the base peak. It's the most plentiful little fragment that gets through. Why do you think we get others? Right, so if we go down below 16, we have one at 15, 14, 13, and 12. Why are we getting other peaks?
I want to say the surrounding
So remember,
charges.
our molecular ion is going to be the original thing intact, right? But once that is formed, depending on how stable it is, it can also further fragment, right? So one of those fragmentations is it can lose a hydrogen, right? So when we have our molecular ion, which had a 16 mass, it can lose a hydrogen, producing a carbocation that's minus 1 hydrogen. What would be the mass to charge ratio for this fragment?
13.
So if we have carbon, 15, right? So then what do you think the 14 comes from?
The loss of another hydrogen.
Loss of another hydrogen. Where does the 13 come from? Loss of another one. We get down to carbon, which is the last one there, okay? So again, our not always the biggest peak, but the peak right before the last peak, that's usually going to be our molecular ion, okay? Everything else is just a fragmentation of that. Yes?
So, in theory, then the first segment or the first line on the graph would be the original.
Not the first, because we'll notice the actual original molecular ion, which is 16, is this guy. It's not the first one on our graph. So there's another peak here,
Right.
which is this guy, and we're going to talk about that in a second, what that comes from.
I meant right after the 10, the really small one. It's around the 12, and carbon is 12.
Carbon's 12, but that's not going to tell us anything about our structure. Okay, so again, anything below our molecular ion is usually fragmentation, just pieces. We've lost a hydrogen, we've lost whatever, okay? There is one thing to note though, and it's this guy that's above, right, which has a mass to charge ratio of 17 for this molecule. Where is this going to come from? So it's okay, because yeah, it's not obvious, and then we'll talk about it in a second, but just note that molecular ion is usually going to be the one right after that original first peak, that tiny little bit. And we'll talk about what we can do with that tiny little bit again in a second. Okay, so what's next? Okay, so number one, I just mentioned that the molecular ion can be the largest peak, can be the base peak in the spectrum. So for example, if we look at benzene, benzene has a mass of 78, I think. So molecular weight of 78. When we look at the mass spectrum of benzene, we find that the tallest peak has a mass to charge ratio of 78, right? So that's great. It's the base peak. It's also the molecular ion peak, okay? Note though for pentane, pentane has a molecular weight of 72. For pentane, is the tallest peak the molecular ion?
No.
No, right? So the tallest peak, or the base peak, ends up being right here, which it ends up being at about 43, whereas the molecular ion ends up being way out here, which ends up being about 72, okay? So just note that depending on the stability of that molecular ion is going to depend on who is actually the base peak. It can be the base peak, but the base peak is not always going to be the molecular ion peak, okay? The molecular ion peak is always going to be the largest mass to charge ratio, again, moving back in 1. Okay, so now, what are we going to do with this? So number one, if we didn't know this, and we had this, what could we determine from these mass spectrums? So we didn't know this, we had this, what would this tell us?
The highest peak is not the mass weight.
But also, what would this tell us?
The molecular
Molecular weight of the compound, right? So if we don't know what we're dealing with, we do our mass spectrum, we get our molecular ion, that's giving us the molecular weight of the compound. That's number one of what this is actually going to tell us. Okay?
So that's I guess like the last peak slash the high, like, yeah, the last peak is
The last
the
cluster
base, or is
The highest of the last cluster.
Okay.
Yeah. Depending. We'll talk about where this kind of changes.
Before, right?
Well, there's some exceptions, and we'll talk about that at the very end. Okay. Okay, so good. Molecular ion. Again, it can be the base peak. It may not necessarily be the base peak, though. But again, what are we actually going to be determining from this? The big one is the actual molecular mass of the compound. So what are you going to do with the mass spectrum? It's going to give you the molecular weight. Okay. A couple of other things that it's going to tell you. If you end up with a molecular weight or a molecular mass of your compound that is odd, that is telling you that there is a nitrogen atom in the compound. Okay? So it's either a nitrogen or it's an odd number of nitrogen. Okay? So that's only if the molecular weight is odd. Because again, nitrogen is what? 14? It just ends up that way. Number two, if you end up with a molecular weight that is even, that tells you that there is no nitrogen in the compound, or it tells you that there is an even number of nitrogen in the compound. Okay, so that's the number one most informative bits of information that we can take from our mass spectrum, from at least the molecular ion peak. So what's next? A couple more things. We're going to go back to that little weird bit at the beginning. This guy, right? So again, for methane, our molecular ion peak was this one, and we abbreviated that M plus the little radical up here. What we call this peak that occurs at 1 mass right above it, we call this the M plus 1 plus with a little radical peak. This is the M plus 1 peak. Now, where does it come from? So again, we go back to this idea of isotopes, right? So carbon-12 had a mass of 12, right? How much, or what is the percent abundance of carbon-12? It's about 98.9% abundant, right? What is the other isotope of carbon? Carbon-13. Carbon-13 has a mass of 13, right? So that mass of 13 plus the 4 hydrogens gives us a mass of 7, or 17, pardon me, right? That is the M plus 1 peak. Now, what is the percent abundance of carbon-13? 1.1%, okay? And so what we will find for this guy is that this M plus 1 peak is 1.1% of our molecular ion peak. And that's because there is 1.1 of those carbon atoms with carbon-13 in them, okay? Now this is kind of the big part. This is what you're really going to get out of mass spec. Depending on the number of carbons is going to depend on the relative percentage that this guy is to that guy, right? So for example, if I had, let's say, decane, which has 10 carbon atoms in it, 22, what we find in this M plus 1 to M peak is that this ends up being 11.11%, right? So if we looked at the peaks, this guy would be about here, where this guy is here, right? Why is it 11.11% of the molecular ion peak?
This is carbon-13.
Because how many carbons does it have in it? 10, right? And each carbon that it has in it is going to always make 1.1% of this peak, right? So if there were 2 carbons, then the M plus 1 peak would be 2.2% of the molecular ion peak. If there were 3 carbons, then the M plus 1 would be 3.3% of the molecular ion peak. So the ratio of this guy to this guy is going to tell us how many carbon atoms are in the compound, which will help us in determining the actual molecular formula of the compound. Okay, so now to demonstrate that, I'm going to do an example problem that you could potentially see in a homework or on the exam. So a lot of times they're not going to actually give you the mass spectrum, right? They're just going to give you the percent abundances or the relative abundances from the mass spectrum data, okay? So in this problem, they want us to use the following to determine the actual molecular formula of the compound, right? So what they tell us here, this is a typo, this is supposed to be a 73, is the molecular ion has a mass to charge ratio of 72 and a relative abundance in the mass spectrum of 38.3%. The M plus 1 peak has a mass to charge ratio of 73 and a relative abundance of 1.7% in the overall mass spectrum peak, okay? So number 1 question that I have for you, is that molecular ion, is it the tallest peak in our mass spectrum if we actually saw the mass spectrum of this guy? What would be the relative abundance if we were dealing with the base peak, the tallest peak in the mass spectrum?
It would be your carbon after 70, well, it's 73.
So this guy, if this was our base peak, the tallest peak in the spectrum, what do we define the base peak to have a relative abundance of? 100%, right? It's 38.3% of that base peak. So is this our base peak? No, right? So that's already something to note, okay? Our molecular ion is not the base peak in the spectrum. Something else is. We don't know what it is, but it's something. Okay, so the first part in determining this or doing this is we need to figure out what percentage this guy is of this, right? How would I go about doing that? If I want to figure out, I have 1.7%, I've got 38.3%, how would I figure out what percentage this is of this?
Divide.
Divide the two, right? So if I take 1.7 and I divide it by 38.3, again, I'm comparing M plus 1 to the molecular ion, and I multiply this by 100, I end up with a 4.4%, okay? Okay, so this says that the molecular, or the M plus 1 peak is 4.4% of the molecular ion peak. So how many carbons do I have in this compound? If I have one carbon, what would be the percentage between these two?
It should be 98, or 1.1.
1.1. If I had 2 carbons, it would be,
2.2.
if I had 3 carbons, it would be,
3.3.
and if I have 4 carbons, it is 4.4, right? So I'm going to take this guy, again, my percentage of this versus this, and I'm going to divide it by that 1.1% abundance. That gives me 4 carbons in the overall compound. Okay, so then, am I done? Is that the molecular formula? I know I have 4 carbons.
No, you need other stuff.
There's other stuff, right? How do I know there's other stuff? How much is 4 carbons? How would I know what the mass of 4 carbons is?
I just lump them together.
Right, so I have 4 times, what is the mass of 1 carbon? 12, so this gives me 48. What's left over? 72 was my actual mass of my molecule, right? That's the molecular ion peak. So 72, that's not a 7, that's a Z. 72 minus 48 gives me 24, so I still have 24 to get rid of. Is nitrogen in this compound?
Is it even or it's even, but it's after 72, so yes. No.
So if it's even, we can't have nitrogen, but how many nitrogen do we have to have? We have to have an even number, so at least 2. 2 times 14 is what? 28. Do we have 28 still? No, right? So can't have nitrogen. If we think about just hydrogen, right, and 4 carbons, the most hydrogen that 4 carbons could have is 10, right? So is that 24? No, right? So what else is there probably going to be? Knowing it's an organic compound, we've got carbon, we've got hydrogen, who else are we probably going to include? Oxygen, right? So oxygen is 16. So 1 oxygen would give us 16. What's left over? So subtract these guys. We have 8. So now could the rest of them be hydrogen?
Yes.
Yes. Okay. So again, the rest of these guys could be 8 hydrogen. So what is the molecular formula for our compound? We have C4, we have H8, and we have O.
Now let's do it over again.
Yeah, there's a practice one. We don't have so much. All right, I skipped ahead. There's a question on the next one that uses the same thing. Okay, so here's a question very similar to the one that I just posted. So we have a molecular ion, right? So here they give you the molecular ion. It's a little radical here. It has a mass of 68, and they tell you that the relative abundance of this molecular ion is 100%. So this is actually the base peak in this example. And then in the M plus 1 peak, we have a relative abundance of 4.3%. Okay, and again, that M plus 1 peak is due to carbon 13. So I want you guys to use this data and figure out what the molecular formula is for this compound, given what's given on this slide. So take a moment, kind of follow a similar procedure that I just did, and then I'll come back for the answer. Okay, so to go ahead and start this, again, for every 1 carbon, right, we're going to see M plus 1 peak of 1.1%, the molecular ion peak, right? The last one we had to deal with was the fact that our molecular ion peak was not the base peak, so we had to figure out the ratio of this M plus 1 to molecular ion peak. But essentially, at this point, we can see it immediately, right? If we take the ratio of the M plus 1 peak right, relative to the molecular ion peak. Since the molecular ion peak is the actual base peak, this ends up just being 4.3% divided by 100 times 100, which just gives us overall 4.3%, right? So if you have a molecular ion that is the base peak, you don't really have to undergo this first step of figuring out the ratio of the n+1 peak to the molecular ion peak, because it's already essentially defined, right? The base peak is a molecular ion. This guy is 4.3% of that, okay? All right, so if the n+1 peak is 4.3%, and we know for every one carbon, it's going to contribute 1.1% to that ratio. So we're just going to take that 4.3%, we're going to divide it by the 1.1%. That's going to give us essentially 4. Right? If we round up, and that's what you are supposed to do for this, guys, round to the nearest whole number. 4.3 divided by 1.1 gives us a, let me go back, this is 3.9, and again, we're going to round up here to the nearest whole number. So you don't always round up, you're going to round to the nearest whole number, but for us, that's going to be up here. So this gives us 4 carbons overall. Okay. All right. So again, for carbons, we know each carbon is going to contribute 12 to the overall mass. So we take the 4 times 12. That gives us 48 with respect to the 4 carbons. But again, the entire mass of this molecular ion is 68. So the difference here, 68 minus 48, is equal to 20. So we have to come up with another 20 AMUs. Again, if we said all of this was hydrogen, there would be 20 hydrogen because each hydrogen is 1. But for 4 carbons, the most hydrogen it can have is 10. So that's not possible. It can't all be hydrogen. So we could say our first attempt, or A, would be hydrogen. It can't all be hydrogen, so we're going to ignore that. We will have some hydrogen, but we'll figure out at the end. B, we can imagine it could be nitrogen, but again, a big indicator that this is not an odd number of nitrogens. Odd number of nitrogens is the fact that this is even. And if we did have an odd number of nitrogens, it would be odd. So then we could say, well, what if there are 2 nitrogens? What if we have an even number of nitrogens? But 2 nitrogens is 2 times 14, which gives us 28, and we don't have 28 left over, right? So that kind of rules out nitrogen entirely. So then the other organic or very heavily used element in organic chemistry is oxygen. So C is going to be oxygen. Oxygen gives us an atomic mass of 16. Right, so we have 20 left over that we still have to account for. There's enough for an oxygen in there, so we can imagine that, okay, we have 1 oxygen, that's 16. 1 oxygen, that's going to be 16. So then 20 minus 16 is going to give us 4 left over. And then at that point in time, we can assign these guys to hydrogen. And there's going to be, again, 4 hydrogen because each hydrogen is 1. Okay, so we have carbon 4 is what we figured out here. We have hydrogen 4, and then we have an oxygen. Again, you could say, well, how do we know it's not 2 oxygen? Well, 2 oxygen is 32, and we still only had 20 to get rid of, right? So it's kind of like a process of elimination using very common elements, carbon, hydrogen, nitrogen, and the fact that, you know, you can only make so many bonds with so many different things. Okay, so last little topic we're going to deal with is something called an n+2 peak. So we just talked about the n+1 peak, right? So we have our molecular ion, right, which is our M with our positive charge, our radical. Again, this guy is our molecular ion, and that's what we keep. Getting the vocabulary with respect to this is kind of important. Our molecular ion or our parent ion, we have just talked about the presence of an n+1 peak, right, which is going to be 1 mass unit more than the molecular ion peak. Again, this is our n+1 peak, and this is due to the presence of that carbon-13 isotope, right, which again is going to be about 1.1% of the molecular ion peak, depending on the number of carbons for every carbon there is. But now we're also going to talk about the presence of potentially an M+2 peak, which is going to be 2 mass units greater than the molecular ion peak. And this is going to kind of tell us about the presence of other things in the compound, okay? So now, remember that for carbon, we had carbon-13, right? That is an isotope that is present in nature. Again, it is going to be, or it has a percent abundance of 1.1%, whereas carbon-12, which is the major isotope, has a percent abundance of 98.9%. So for the most part, we find carbon-12 in all of our compounds, right? There are other isotopes that are present in a couple of our ionic or a couple of our organic compounds. For example, hydrogen has a couple of different isotopes. So hydrogen 1 is just normal hydrogen. We do have an isotope of hydrogen called hydrogen 2. This is deuterium. And then we also have an isotope of hydrogen that's hydrogen 3. This is called tritium. And again, all they differ in is the number of neutrons in the nucleus, right? Hydrogen 1 has 0 neutrons, hydrogen 2 has 1 neutron, and then hydrogen 3 has 2 neutrons. And again, that other mass is coming from the proton. Now, these guys, deuterium and tritium, they don't have very high percent abundances, so they're not going to actually affect our mass spectrum. But there are other elements that are going to be important that do have isotopes that are going to have a signature on our mass spectrum, right? So one of those is chlorine, right? So there are 2 abundant natural isotopes of chlorine. The first one is called chlorine-35. And again, chlorine has 17 protons in the nucleus, right? So chlorine-35 therefore has 18 neutrons. And there is another isotope of chlorine that is also has a high percent abundance. This is chlorine-37. Again, which has 17 protons in the nucleus. This guy now has 20 neutrons, okay? All right, so if you did have a compound that had chlorine present in it, again, both of these isotopes have high percent abundances, and we'll go over that percent abundance, then you would not only have a molecular ion, which we're always going to have a molecular ion. You would also have an M+1 peak due to the presence of carbons in your compound, but you would also now have an M+2 peak because, again, a certain number of your molecules are going to contain this guy, and a certain number of your molecules are going to contain this guy, which is 2 mass units greater than the chlorine-35, right? So the percent abundances here are going to be kind of important, right? So let's say that you had a spectrum and you come over here and you don't necessarily know what's in this spectrum, but you do find that you have a molecular ion peak at about looks like 112, right? And then you have, again, right next to it, an M+1 peak at about 113, right? And then you have an M+2 peak at about 114. Okay, the presence of that M+2 peak tells you that potentially chlorine is in the molecule, right? So if there is an M+2 peak, it could potentially be chlorine. Now, if we go back to these percent abundances, we find that chlorine-35 has a percent abundance of 75%, whereas chlorine-37 has a percent abundance of 24%, all right? So if you do have chlorine in your molecule, this M+2 peak is going to be, let me actually get the notation correct here. This M+2 peak is going to be approximately 24 plus 0.2 divided by 75.8, which is approximately 1/3 of your molecular ion peak. So 24.2 divided by 75.8 gives us about 24.2 divided by 75.8 gives us about 32% multiplied by 100, of course, right? So if you look at the spectrum and you find your molecular ion peak and you find that you have an M+2 peak and you find that this guy relative to this guy ends up being about 32%, that this peak relative to this peak is 32%, then that's a big indicator that you have chlorine in your molecule. Okay, so then the last one that could potentially give an M+2 peak is bromine. So bromine has 2 isotopes as well. So we have a bromine 79 and we have a bromine 81, right? Again, these are our 2 isotopes of bromine. So let me just write that, 79 bromine and then 81 bromine. Bromine has, I can't remember. Bromine has 35 protons. So 79 minus 35 is 44 neutrons. For our bromine 79 isotope, it's got 35 protons. So then the bromine 81 isotope has 46 neutrons, right? Again, there's a difference here between the two of 2. So if you had an M+2 peak, right, it could also potentially be bromine because, again, we have 2 major isotopes and their difference in mass is 2 mass units, right? So let's say that you came in and you said, okay, well, I've got a molecular ion peak here, right? I go just to the right of that. I got my M+1 peak here. And then just one more to the right, I've got my M+2 peak here. So this is going to be my M+2 peak. And again, this is my molecular ion peak. Now, the question is, well, I have an M+2 peak, so it could be chlorine. But we've also said now it could be bromine, okay? The question is, well, how do you know the difference? And the difference comes from those different relative proportions of the 2 isotopes. For bromine, 50% of the time, we're going to find bromine 79, but then 50% of the time we're going to find bromine 81, right? So if you come in and you compare the relative ratios of this M+2 peak to this molecular ion peak, and they're about approximately 50-50, then that tells you that this has to be bromine, right? Because if it was chlorine, the ratios of these two would be approximately 33%, right? So how do you know the difference? Is it chlorine? Is it bromine? You're going to compare the relative amounts of this M+2 peak to the molecular ion peak, and that should be a big indicator whether or not chlorine or bromine is present in your compound. If it's bromine, it'll be about 50%. If it's chlorine, it'll be about 33%. And again, this is for every bromine and every chlorine. Okay, all right, so that is the end of what I have to talk about with respect to mass spec stuff. So now we've finished IR spectroscopy. We've finished mass spectrate data. The last spectroscopy that we're going to go into we're going to go into next, or starting on whenever. But it's actually going to be kind of the most important of our spectroscopy techniques, and this is going to be NMR spectroscopy, okay? So do the homework, email me if you have questions, and then once we finish NMR, we're going to be pretty much done with the semester. So fingers crossed, we're almost done. Okay.